Welcome back. Next thing we're going to look at is mathematical induction. It's a very important technique of proving universal statements about the natural numbers and some closely related things as well. Suppose we have a statement like this one, for all n in n, something or other. Those dots just represent some statement involving a variable n. So it could be, for example, one we've seen before, n cubed congruent to n mod 6, for example. And the way we prove that by mathematical induction is the following. First of all, whatever statement we have here, we prove it's true when n equals 0. Secondly, we prove that if the statement is true for some particular value of n, then it's also true for the next value, n plus 1. Why does this work? Well, you'll see an analogy more or less any way you look about toppling dominoes. So I'll give you a slightly different one. Suppose that you're reading a book. Suppose that you read the first page of the book. And suppose every page of the book is so exciting that once you've read it, you have to read the next one. Then clearly you're going to end up reading the whole book. Same thing here. If we prove the statement is true in the first case, that's n equals 0, and if we prove that whenever it's true for one case, it's true for the following case, then it must be true for every possible case. In other words, for every value of n, 0, 1, 2, 3, etc. There's no particular need for it to start with n equals 0. Suppose I have a statement like this one, for all n greater than or equal to n naught, so starting somewhere other than 0. Again, ... means some statement about n. You can prove that by mathematical induction. The technique is really exactly the same, one very small difference, which is that you have to begin by taking the statement and proving it when n equals n0, not just for n equals naught. And the second step is the same. Prove that if the statement is true for some particular value of n, then it's true for n plus 1. Whichever way you do it, whether it's this first format or the second format, step 1 is called the basis of the proof, and step 2 is called the inductive step. Let's do an example. And this also, if you see anything about induction anywhere, this will be pretty much the first example you see. So let's do this one. I will try and do some less common examples later on. So we're going to prove that for all integers n from 1 onwards, if you add up 1 squared plus 2 squared, etc., plus n squared, the formula for the result is 1/6 n times n plus 1 times 2n plus 1. So first of all, we have to do the basis step. We're starting here with n equals 1. So n is greater than or equal to 1, so the first value is n equals 1. And that's the first thing we have to do. The basis step will be to prove that the equation is true when n equals 1. Now, if n equals 1, then this left-hand side here is simply 1 squared, which is 1. And the right-hand side here is 1/6 times 1 times 2 times 3, which is also 1. So the statement is definitely true when n equals 1. So let's now assume that the statement is true for some specific value of n, which is 1 or more. Please be careful to write it this way. If you don't write that we're assuming it's true for some particular value, then that makes it sound like we're assuming the result is true for all values of n, and certainly we can't do that because, of course, that's exactly what we're trying to prove. So we're going to assume the equation is true for some particular value of n. In other words, we're assuming that this equation here is true. Remember, it's for a specific value of n, not for all n. We've got to prove that the result is true for n plus 1, which is this here. Okay, so we have to use this first equation here in order to prove the second one. Now we can do it the following way. Looking at this second equation, we'll just prove that as we often do for an equation. We'll take left-hand side equals, 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 etc. until we get the right-hand side. The left-hand side is this one. This left-hand side here. And I'm going to split that up as 1 squared, etc. plus n squared plus the last term. In other words, I'm splitting off the last term here. Why do I do that? Well, because of course I have my assumption here. I have my assumption that 1 squared plus 2 squared, etc. plus n squared is given by this formula. And so therefore, when I have 1 squared plus 2 squared plus n squared further down, I can just substitute this left-hand side into there. So this 1 squared plus 2 squared, etc. plus n squared becomes 1/6 n, n plus 1, 2n plus 1, and I've still got the plus n plus 1 squared. And we have to prove that that equals the right-hand side here. So if I just simplify this last expression, what we should notice is that both terms here have a common factor of n plus 1. It'll be handy to take that out. It'll also be quite handy, probably most of the time, to take out any fractions that you can see there. So I'm going to take out a common factor of 1/6 n, n plus 1. If I do that, what's left in the first term is n times 2n plus 1, and I've written it here. And what's left in the second term is just an n plus 1, together with a 6 to cancel out the 1/6. So I get that one there. Okay, so if I then expand the quadratic here, I've got n times 2n is 2n squared, n times 1 is n, plus another 6n makes 7n, and 6 times 1 is 6. And I can factorize that as n plus 2, 2n plus 3. And that's exactly what I wanted, because my aim was this here. 1/6, got that. N plus 1, got that. N plus 1, that's of course n plus 2, so I've got that. 2 times n plus 1 is 2n plus 3, so I've got that. I've proved left-hand side equals right-hand side. So we're looking at this particular equation for the sum of all the squares from 1 squared up to n squared. And we've shown that that's true for n equals 1. We've shown that it's true for any specific value of n, then it's also true for the next value. And by induction, that proves that it's true for all values of n from 1 upwards. As we always do, let's have a few comments about things we can learn from this. First of all, general format for an induction proof. It'll usually look something like this. Let n equal 1, or whatever. It might not be 1, it might be 0, it might be anything in principle to start with, but let's say 1. Let n equal the first value. Then after giving some argument, here, we conclude that the result is true for n equals 1. We'll then assume that the result is true for some particular n or for some specific n, and we have to prove that the result is true for n plus 1. We go ahead and prove that, and we've done it. And by induction, the result is true for all n greater than or equal to 1. I'm writing down here what we have to prove, so we must prove that something or other, and then after we've assumed something else, and that's exactly what I did here. It's not obligatory, but I think if you have it this way, we're assuming this here, and we want to prove this one here. So you've got the assumption and the aim right there on the page in front of you, and I think that makes it very easy to be clear about what you're assuming and what you're trying to prove. When can you use induction? When can you hope to successfully use induction? Perhaps it would be a better way to put it. Well, we need some fairly simple relation between the statement for n and the statement for n plus 1. So here's an example. Suppose we're looking at one that we had earlier, which was that the nth root of n factorial is less than the n plus first root of n plus 1 factorial. Okay. If you remember way back, we proved that for n equals 8. I suggested you might like to try it as an exercise for any value of n. Could we do that by induction? Well, if we're going to do it by induction, then we have to make this assumption. We have to prove that that implies the same for n plus 1. In other words, we have to prove it implies the n plus 1th root of n plus 1 factorial is less than the n plus 2nd root of n plus 2 factorial. Now, I guess that's fine as a proposed project, but it doesn't look very likely to be successful. Because for a start, what do we know about the n plus 1th root of n plus 1 factorial? We know from here that it's greater than something, and we're trying to prove it's less than something. So that looks like it's going the wrong way around. And if you try and write, for example, the n plus 2nd root of n plus 2 factorial in terms of the n plus 1st root of n plus 1 factorial, then it just doesn't seem to work. The algebra just seems to be too messy. So a statement like this, while I guess it's perfectly possible in principle to prove it by induction, it doesn't really look as if that's going to be a successful way to go. So just to recap, to make the method of induction work, we need some fairly simple relation between the statement for n and the statement for n plus 1. Here's something for you to think about. What's wrong with the following as an attempt at part of the previous proof? So I'm going to say we've assumed that 1 squared plus 2 squared plus n squared is 1/6 n plus 1, 2n plus 1. And now I'm going to just substitute n equals k plus 1. And so therefore I get 1 squared plus 2 squared, etc. plus k plus 1 squared is equal to 1/6 k plus 1, k plus 2, 2k plus 3. Done. Not done. Why not? Well, if you had the chance to think about that a little bit, remember the point is that we're making this assumption here for a particular value of n or a specific value of n. And if it's true for a single specific value of n, then we can't substitute a different value of n like k plus 1 into it. So that's not a correct way of doing induction. Here's another example. So let x be a real number between 0 and 1. And then I'm going to say that for all integers n greater than or equal to 0, 1 minus x to the power n is greater than or equal to 1 minus nx. So first of all, we'll start with saying x is a real number from 0 to 1. And now I'm going to prove the statement by induction. I'm starting off here. This is supposed to be true for all integers n greater than or equal to 0. And so the first value is 0. That's what I have to check for the basis case. So if I look at the basis case here, when n equals 0, this is saying 1 minus x to the 0 is greater than or equal to 1 minus 0x. In other words, it's saying 1 is greater than or equal to 1. And that's clearly true. So that's the basis step done. Now for the inductive step, we have to assume the result is true for some specific n greater than or equal to 0. In other words, I'm going to assume this one here. And my aim is to deduce the result is true for n plus 1. In other words, I have to prove this here. As I mentioned before, I strongly recommend writing out your proof in this way, because then we have here right in front of us, this here is what we're assuming, this here is what we're aiming to prove. So how can we do it? What can we do with this inequality here? How could we start? Well, let's start with the left-hand side. I'm looking at 1 minus x to the n plus 1. And now, using this assumption, I can get my 1 minus x to the n plus 1 by multiplying both sides by 1 minus x. Before we do that, we should be cautious, because remember, if you have an inequality, you can multiply both sides by the same quantity, provided that's a positive quantity. However, remember x is between 0 and 1, so 1 minus x is a positive number, and so we can multiply both sides of the assumption. That's this one up here. Just disappeared. We can multiply both sides by 1 minus x to get this here. Next step. And now the left-hand side is exactly what we want, like that left-hand side there. And so let's expand the right-hand side and see what we get. Well, we just multiply out. We get 1 minus x minus nx. That's where the minus n plus 1x comes from. And we get minus x times minus nx, which gives us plus nx squared. Now, our aim is to show that that's greater than or equal to 1 minus n plus 1x. Well, just look carefully. What have we got here? We've got our 1 minus n plus 1x, and we've got plus nx squared. That is greater than or equal to 0, and so therefore if I delete it, I get something smaller. So this is greater than or equal to the next one, 1 minus n plus 1x, and we've finished. We've shown the inequality is true for n equals 0. We've shown that if it's true for some particular n, then it's true for n plus 1. And by induction, the inequality is true for all integers n greater than or equal to 0. What can we learn from this proof? Notice here we have a doubly quantified statement. Remember quantifiers. In this case, we're using quantifiers for all, namely universal quantifiers. We've said for all x, specifically for all x from 0 to 1. For all n, specifically for all natural numbers n, 0 upwards. Now, how have we done that? We've looked at the for all x. We've done that as in earlier proofs. We just begin by saying let x be whatever it's supposed to be. So any number from 0 to 1 in this case. And with the for all n part of the statement, we've done that by induction. As I mentioned before, to do induction successfully, you need to have a close connection between the property for n and the property for n plus 1. In this case, just the left-hand side for n is this one here, 1 minus x to the n. The left-hand side for n plus 1 is this one here, 1 minus x to the n plus 1. And there's clearly a close connection between them in that you just have to take the first one and multiply by another factor of 1 minus x, and you get the second one. And third comment, I mentioned this before, but it's worth repeating. If you've got an inequality, you can multiply both sides of the inequality by the same thing, as long as that's a positive thing you're multiplying by. So never multiply an inequality by anything unless you know for sure whether the thing you're multiplying by is positive or negative. If it's positive, you just do it. If it's negative, you have to reverse the inequality.